This is the uh, fourth lecture. This is the video recording. So after we know the material that move one, basically that is the smart materials classification based on materials and based on stimuli. There's one video here. This is about the just the material science introduction. Okay, so I will skip all the video. You can watch it in the file. So just open the Prezi file that I prepared and watch the video. Okay, so we go first to smart memory alloys. Okay, because the SMAs or smart memory alloys is the earliest smart material or shape changing smart material, and it is like the most familiar type. Okay, so I've shown you the nitinol, so let me show you how the memory effect. Okay, so all types of recoverable strain, including elastic deformation, inverse piezoelectricity, and electroactive response of certain polymers, are considered to demonstrate the shape change effect. So, elastic deformation, you have the materials, you applied force, and the materials deform. Okay, but when you remove the force, the materials revert back to the original shape. Inverse piezoelectricity, from strain to electricity and from electric to displacement, and etc. Okay, so shape memory effect is the ability to switch predetermined form upon a change of temperature, stress, or magnetic field. Yeah, this is the mechanism. So if we see the thermodynamic view, okay, we see here from the graph, this is the free energy, this is the temperature. Okay, the M meaning the Martensite phase and A is Austenite phase. So here is the change from the parent, okay, from the Austenite to Martensite, and this is from the Martensite to the Austenite. So you see there is a gap here. Okay, so the conclusion from the graph is the free energy in the martensitic phase is higher than austenite, and the state is a metastable equilibrium. So what does that mean is, if you have a metastable equilibrium, it is easily to be disrupted. Okay, it's not stable. So which means when you have materials in this condition, you can change the structure, the phase. Okay, the phase changed the inside of the structure, and then you can predetermine the form, and when you hit back, okay, increase the temperature, it will went back to the original shape. Okay, so meaning the higher energy is less stable than the lower energy. So when you have the deformation, and then you heating the material, increasing the temperature, it might change the shape back to the original shape. Okay, Yeah, this is the conclusion. So in this shape change effect, the reversal occurs without additional energy. So when the force is removed, the spring will return, and when a bimetal is cooled down, the shape change will be reversed. So in SME, there are two-way, okay, uh, or more, okay, at least two, one-way shape and two-way shape. So one-way shape, the material is given a form at the elevated temperature and then quench. Quench means cooling down rapidly cooled down, okay, to ambient temperature. When heated, it returns to its high temperature shape. Okay. So it's only one way. Okay. In two way, uh, the material is programmed or trained, okay, to remember both high temperature and low temperature. So this material has two conditions, okay, to shape, okay, to state, let's say states, okay. So high temperature and then low temperature, and it can be cycled between these two. So if you change the temperature, maybe increasing, it will be the higher temperature shape, and when you lower it down, it will be low temperature shape. And several materials, it can have several shape transitions, okay. Yeah, mostly in the polymers, okay. And the key for the alloy is, yeah, again, it's martensite and the austenite, okay. So it has this hysteresis. So this hysteresis, okay, uh, it is the gap of uh, the free energy, okay, the free energy. So that's why uh, when the alloy is heated, okay, the martensite starts to transform into austenite phase. Okay, so let's see here. This is the martensite. Okay, it's heated here. Go to the austenite phase. Okay, and then it will transform, going here, and then finish here, become austenite. Okay, and then when it's cooled down, okay, it will be reversed. So from here, going here, cooling down, cooling down, cooling down, and here. This hysteresis is actually telling us that there is slightly difference in energy or in thermodynamics. Okay, meaning the shape inside the austenite or martensite is different because of that. Okay, yeah, and how many percentage of martensite uh, can be finished is depends on uh, this cooling down process. Okay, if we see how the cycles, okay, so from the martensite, heating become austenite, cool down, it has this structure. We perform some force here to deform this material, okay, become here, and we heat it back, and it becomes the original shape. So the key is when you increase temperature, the material, the alloy, uh, going back to the austenite, okay, and when it cool down, in a quench process, it will be go for martensite. So in the market or in real life, this part, this martensite is the product. Okay, so when the product deform, it's become like this, and if the temperature went back to this austenite and then cool down. Okay, it can be transformation, it can be one way, two way, or multiple ways. So one way, maybe you just set up the austenite temperature, this shape. Okay, and two way, maybe you prepare the austenite and the martensite. It has fixed structures, or fix the shape. Okay, fix the shape here and here. So that's the alloy. And then for uh, the polymers, it has more flexibility in design, and because it is uh, less costly than the alloy, it has many possibility and variations. The important polymers in here is the cross-linked polyethylene, amorphous polymer primary polyurethanes. And this is the why we are choosing the polymers over the alloy. The density is much lower, larger strains, so it can undergo really elastic or plastic deformations. Okay. Manufacturing process is much cheaper, lower energy, lower pressure, and easier to be trained or to be programmed. And see the mechanism, we have two mechanisms here. Dual state, meaning it has two conditions. Okay, the first, heating the polymers until the transition point. It can be glass or melting. Okay, and above this temperature, the polymer can be shaped plastically, so we can deform the polymers into a new shape. Okay, if the new form is maintained by constraining the polymer under force, cooling below the transition point will freeze the temporary shape and result in stiff part. When it is reheated, it will revert back to original shape. So uh, you go for the deformation. Okay, shape plastically into new shape, and then maintained by constraining the polymer under force, and then cool down. And when you cool down, that part becomes stiff. Okay, really stiff. But when you heat, increase the temperature, you'll be back to the original shape. So you have dual state. Okay, dual state here. And the second one is the dual component. Okay. So component means the material or the copolymer in this mechanism at least having two segments. So two segments. One segment is having the high softening temperature, while the other, it can switch from hard segment to soft segment. Okay, within the temperature range, and as a result, the polymer can be plastically shaped above the temperature transition. Okay, where the transition segment is soft. Okay, the overall shape is fixed when the temperature is below the transition point. Okay, so when above transition point, you can plastically shape. Okay, uh, because this part, okay, in the above transition point, the transition segment is soft. Okay, so you have the uh, high softening temperature one segment, and the other, it can switch from hard to soft. Okay, so you have to do dual component or two component here. And there's the example for stimuli. It can be light, can be heat, okay, temperature. or indirect stimuli, like for example infrared, a magnet, electricity, all is actually increasing temperature, but you are using the other stimuli indirectly. um, the model, okay, uh, the point in the model of the shape memory in polymer, we have the net points, okay. It is the intersection, okay, the intersection that determine the permanent shape and link the polymer network, and it depends on polymer type, okay. The net points, it can be bonds, okay, it can be covalent, weak, one van der Waals hydrogen bond, crystallites, or ion rich domains. And the molecular switches are segments that temporarily fix the desired shape obtained by deformation. So it can go for phase transformation. This molecular switch, they can change from melting and then solidified, glass transition, liquid crystalline transition. These segments can be amorphous crystalline or liquid crystalline. And the third one is ceramics. The ceramics, as I mentioned maybe in the previous videos, they are brittle by nature and having the low tolerance for tensile or bending stress. So it's not really good candidate, but we have uh, we have a new development for ceramics, so we can use also in smart materials. So the first demonstration of the ceramics in the research is for using the zirconia polycrystal, but because the macro cracking was observed, and then they developed another new material and etc., and they found that the actually the phenomenon is because of the thermally or stress induced martensitic transformation of zirconia crystal, so they have the property. And then the composites and hybrid, okay. uh, yeah, it can be any combinations, okay. This is the example: silicon 30% melting glue and silicon paraffin wax, etc. You can read this and maybe you can find another one, okay. This is just the additional examples. It's not really the segment or the section, it's examples. And then the fluids, okay, this electromagnetorheological fluids, okay. This is colloidal suspensions. See here the magnetorheological fluids, okay. So you have the carrier, you have the magnetic particles, this dot, black dot here, okay. When you give the magnetic flux or magnetic field here, it will arrange some structures here. It depends on the direction of the magnetic flux, okay, and it will arrange based on that magnet, okay. So these fluids, okay, it usually, or the main components of these fluids is, first is the fluid itself, okay. We call it the carrier fluid, okay, usually oil or any type of oil, and then non-conducting particles, okay, and it need to be sensitive, okay, either for electrical, so you have the electro, or magnetic fields, the magnetorheological fluids. And then you have the third component, which is important here. It's called the surfactant, or you can say surface active agent. It can be oleic acid, citric acid, etc. It is added to reduce agglomeration and the rate of particle deposition. What that means? So this is the surfactant. So surfactant, it has this red, okay, this red head, okay. it is the hydrophilic parts. Okay, and this blue strand line here is the hydrophobic parts. So basically it's like detergent or soap. Okay, when you wash your hand. So the idea is you want to remove oily parts, right? Like a dirt, or maybe after you eat or having lunch, your hand is dirty, and you wash with water and soap. So the water and soap, it will mix together. The water part, the hydrophilic parts will attach or uh, mixing with the water, and the oily part here, the hydrophobic part, will mix with the dirt. So at the same time, the dirt will be attached here, and then the water will wash all oily or dirt, remove all from your hand. Okay, and that's when you put your water. So the same idea is used here. Okay, so this part, okay, the oily part will attach to the fluid. Okay, so you can have really good uh, distribution of these particles, the dot, this black dot. So it can have a good distribution. Okay, or maybe if you have heard the emulsifier, that's also uh, works like the your detergent. Okay, so basically emulsifier is for mixing. Okay, so to mix water and oily part, usually in ice cream. Maybe if you've heard gelatin, and that's one of the example of the emulsifier. So the examples is ferrofluids, is specific type of the magnetogeological fluid, and usually it's from this picture. Okay, this is called magnetite. Okay, uh, usually it's a powder. So um, you have the powder, you have the oily part, and you can get the ferrofluids, and it's quite strong. Okay, uh, so it can keep its fluidity under a strong magnetic field. Usually, in other case, they are uh, becoming solids, but this specific ferrofluid is not. You can watch this video. This quite interesting experiment to see how ferrofluids works, but I will skip it this time. Okay, please watch it. Okay, and then the last part is the electroactive polymers. Uh, Electroactive polymers is important class for shape changing materials because they are flexible, easy fabrication, and low density. This is interesting, but I think you can watch by yourself. It is to show how the polymers works and how you can apply these polymers. Okay. So that's all for this video recording. I hope you get uh, idea, okay, uh, from the several examples here. Okay, so after this section, we will go for the biomimetic. Okay, there are several parts there, and then maybe after biomimetic we can go for the manufacturing. So I hope uh, you can learn more, yeah, maybe finding new inspiration from this course. uh, and I think that's it for this recording. Thank you for watching. Okay, see you in the next video.